Howdy, I'm Braden Seaborn, founder of Innovations, and this video is to pretty much kind of show you around FireEngine and how things work behind the scenes. So, FireEngine is a Python-based game engine that uses Arcade and OpenGL and is currently open source. So, if we come here to our repository, you can use it. I still need to come back here and do some stuff here in the repository, but um, it is open source. In fact, you can also access our demo project right here, which is also built into an exe. So it's pretty cool. So best place to start off is main.py. This is where things start. Pretty much this is where everything is initialized, or everything comes together. So you can see that all our modules are being imported in a specific order, starting with the core engine functionalities, and then moving into all scripts from the game, and then all scripts from any mods that are installed. Which this engine does have native modding support as well. Since it's Python, it's relatively easy to get a mod working. Just drag and drop a Python file. And here, the game loop is initialized. Here's the definition for that class. Pretty much just making that work, taking care of inputs, and also taking care of when the window closes. So not really much going on in the main.py, but nonetheless, it's still very important. We come here to the main FireEngine directory, and here, if you see, there is a FireEngine directory and a game directory. Everything in this game directory is resources that are used in the game. So, for example, assets, any code from the game, object definitions, and so on. And when you build the game, this file right here, game, give me 1 second. I'll open a window. This game directory right here, if we come to the built directory, internal game right here. And it's the exact same folder. And in fact, in the built version, if you change anything in the assets folder, it'll reflect stuff in the game. So, for example, you can change out the textures for the guards. You can change out the sounds. You can change out the wall textures. In fact, you can build a whole entire new scene if you want to, just by changing out the assets folder, which allows for custom mods to very easily be built pretty fast. You just got to have the assets and the definitions in the dat files. Um, so let's actually start with the objects. Say I have an entity that I want to define guard, right? This right here is the guard definition. And in fact, this is actually an INI file, just renamed to .dat. So just so y'all know, it uses the INI system. We can see it's defined your type, entity, and the name. And the names for all objects are very important. Internally, the names is what is actually used to pretty much reference each object. So if two objects of the same type have the same name, there will be conflicts. So for example, if I have a guard in guard.dat, if this is named guard, and in ssguard.dat, it was also named guard, the guard right here would not load, and every single tile that has a guard in it will be undefined, and you'll get the pink and black checkerboard pattern there instead, because the game doesn't know what to load, so it loads that instead. I've actually done that before. That's why I know that happens. I've done it before. So, and same thing. If I were to change anything in here, like for example, the animation path, it would reflect in the game. I can change the damage. I can change the hitbox size. I can change how frequently it shoots, how much damage it does, the health. Um, the how far it can see, how long it waits to go onto each patrol, you can change the sounds. You can do a lot pretty much. And same thing with the guns as well. Like I'm here, pistol dot that. I can change the fire animation. I can add new guns very easily, and you can have a maximum of 10 guns, 0 through 9 on your keyboard, or 1 through 0, I guess. Um, and yeah, you can have 10 unique guns in the game currently. Droppable, same thing there. You have a lot of customizability, and you can replace it. I mean, you can do whatever. I mean, it's open source. And then yeah, here in the test scene, yeah, this right here, this is the definition for the scene that's in the demo. It's the exact same scene. You can see it's just a bunch of text. That's all it is. And so you can just change anything on here and it will reflect on the map. So for example, if I in my .scene file here, so this asterisk right here, that is the player. That's where the player spawns. If I do a little $sign right there in front of the player, $signs are represent guards. So a guard will spawn there. So if I then come back here to main and press play, press run, wait a second. Whenever I load in, there'll be a guard in front of me. Right there. Now, the only things that you can't customize are the ceiling texture, the floor texture, and also the music and the UI. That really can't be changed. That's currently hard coded into the engine. Unfortunately, I haven't had the time to really implement any of those systems. So, but everything else works though. So, and then yeah, right here, yeah, this is the engine right here, FireEngine. So core, this is where all of the core systems lie. So for example, the decorators, the game manager, uh, multi-threading, the scene file, um, and also especially rendering. Rendering is really important here. Most of my time has gone into building a strong rendering engine. So let's start with the manager. This is pretty important. So there are two custom or actually we start with this. So there are two custom decorators. They have a singleton and a register. A singleton, if you know anything decently well about programming, a singleton is just a object in object-oriented programming. Pretty much, a singleton is a class that there can only be one instance of. You cannot create multiple instances of this class, and since the whole entire game engine uses object-oriented programming, um, for certain classes, having just one instance is really important so you don't screw up any references. And that's what that pretty much allows. Just it helps to reduce bugs, it helps to prevent bugs, and make the game engine a lot more stable. This register decorator right here is very unique. So say let's go to entity, right? You can see here that this class, and this is the definition for all entities, um, there is a register decorator. So pretty much what this does is whenever this class is instantiated, it's automatically registered to the game manager. And what the game manager does is it looks through that class and looks for certain functions, for certain function names. So, for example, on update is an example. If it inside of your class, if you have a function called on update, and have the parameters self and delta time, this update function will get called every single frame, and then delta time will be passed through, and you can use that in whatever calculations you're doing. This is called completely automatically. You don't have to worry about calling it; it's just done for you. And there's a bunch of other um, uh, built-in functions as well. So if I go back to manager, we have start, on update, on render, on move up, on move down, on move right, on move left, on turn right, on turn left, on shoot, on interact, and on change weapon. Those are all functions that you can call inside of your scripts. Um, so really, really cool. Multi-processing. We tried to implement multi-threading with our previous rendering system. That didn't work, but we still have this here. So now let's do a deep dive into the rendering engine. This is the main interesting thing about this engine. That's really what makes it unique is the rendering and not necessarily anything else. So there's just one script, one class for the renderer. And yeah, here you can see I'm using a singleton. So there's just one rendering class. You wouldn't want multiple rendering classes. That would cause a lot of slowdowns. Um, but here we can see, yeah, it's also tagged with at register, so it's also registered as well. Um, and so pretty much we have different types of objects. For example, we have objects, 3D objects, walls, and then also floor and ceiling, and also sprites as well. And sprites, that's done separately. So we pull up the sprite entity. Yeah, sprites and entities and droppables, they're pretty much all the same in terms of the class and the logic. It's very similar, very similar stuff, especially when it comes to rendering as well. It's pretty much the exact same thing. Um, so right now, and this is something that we're going to be changing, is the only thing that's actually fully rendered on the GPU is the floor and ceiling. The walls and the sprites, the way that works is the whole entire screen is divided up into a certain number of sections. So, for example, in this case, it's 250. There's 250 rays across the whole entire screen. Um, and when those rays are cast out, when it hits a surface, it first of all sees how far away that surface is, and that's used to determine how high the slice is, and then it's also determines where on the texture it hits, um, and then from there it creates a 1 pixel wide slice of that texture, and that is then queued in our batching system to then be sent to the GPU when we are rendering that frame. So on the on render function here, we can see that we clear the Z buffer and we clear uh, uh, batching stuff. We render our objects and then clear our lists here, and then we have our frame. It's on screen, and then when the next on render loop comes around, it keeps doing it over and over and over. And yeah, if we come here to the draw walls function here, casts right from the player's position and renders the wall with the correct depth. Here's the actual logic here, and this is the exact same logic that is used to render stuff in Wolfenstein and Doom. Doom that does it a little bit differently, of course, but it's pretty much the exact same logic with a couple of minute changes. So yeah, our walls is not completely software rendering. We're still using the GPU to actually render the final frame. We're just sending it a bunch of sprites pretty much every single frame, which is very costly. But we haven't really had a chance yet to turn that to an actual shader. And that's our next goal is to use hardware rendering for everything else. And then yeah, we can see here calculating the step direction, performing our digital differential analysis to figure out where we hit, calculate the distance from the player using the perpendicular distance correction. And yeah, I spent a while in this code figuring out like originally sprites and walls they were rendering weird. Um, and comes to find out that I'm actually using two different rendering methods for the walls and the sprites. So I finally correct that now using the exact same method. Um, so not any visual problems anymore, thankfully. Um, and just some more corrections, some more logic. And this is all done per slice, by the way. This is a lot of logic, especially for Python. Um, and in real time too. Um, and yeah, this right here loads the texture, and then this right here crops it, and then we append it to our draw list so we can do batch calls. So the walls, those are rendered in a single draw call, which is really good. That's good right there. It means that we get a better performance. And then we have a viewport thingy here. Uh, man. GLSO. Yeah, let's just go share loud. Eh, I forget the exact name of the language mode in here that works with this. There it is. HLSL. That's the one that marks it up correctly. Anyway, we create a viewport using a vertex shader, pretty much just a quad that covers the whole entire screen. Pretty simple. It's not very complicated. Then here is our floor shader, and the only real difference between our floor shader and our ceiling shader is going to be should be right in here if I'm correct. Yeah, right here. So yeah, right here. This p-value. Whenever I was originally working on this shader, converting it is originally we were doing software rendering for the floor and ceiling. Um, However, it's a bunch of per pixel operations. We couldn't do a hybrid between software and hardware rendering. It had to entirely be software. So, and Python's really slow, and um, computer screens now are pretty big. So that didn't really work. So I converted it to a shader instead. And this value right here, this is the only difference between the shaders is the naming of some things and this p-value. It's just for the ceiling is positive, for the floor it's negative. All that does is just render the floor and the ceiling in the correct place. So, and we're going to be creating another shader um, for for the walls and sprites. Now, let me see. Draw objects. So this right here is where we're actually drawing our sprites, our entities, our droppables. Um, and so pretty much every single frame, we're taking all these lists right here, which, by the way, I'm gonna click on that. It's not. Okay. Objects. Anyway, we pretty much in the droppables, entities, and um, sprite scripts, there is a there's a list that contains um, every single object of that type, right? And pretty much whenever we are rendering them, we take all of them. These like they all have the exact same. It's like all the classes for each of those types. Um, they're all pretty much they're all very similar. And so pretty much we just combine them into one large list and we render out the objects. And first we have to sort them uh, based on distance. So ones further away get rendered first, and ones closer get rendered last. So uh, back to front rendering is what we do for those objects. Um, and then, so there's also a Z buffer. We have a Z buffer. And whenever we are rendering the walls, we write to that Z buffer. That's the only time that we write to that Z buffer. Um, and the only time that we read from it is when we are rendering out our objects, our entities, our sprites, our droppables, all that stuff. And so the objects they're also split up into 250 slices for the whole entire screen. And I'll show you that here in a second. And it renders similarly to the walls in that regard. But we read the Z buffer, um, and also of course we render back to front as well. So you can kind of see what we're doing here, checking to see if it's in front or behind the player, projecting onto the screen. Um, and then this right here is where we actually start rendering each vertical stripe using the Z buffer. You can see the logic here. And then that gets appended to the draw list as well. And when we are rendering it every single frame, that just gets sent off to the GPU in one large draw call. So yeah, you can see here where we're loading our texture and getting everything from it. And this can be done uh, better, and that's what we're going to be doing with the shader. We're going to have the shader take care of all this. And yeah, you can see here that's being turned into an image, which is then pushed to the draw list. So that's pretty much our whole entire rendering system right now. I'm going to be figuring out a way for us to define and render quads to the screen, is pretty much going to be used for doors and for other very rudimentary 3D models in the world. I'm also really considering figuring out how I can implement some sort of verticality, so the player can go up and down, which is going to be a nightmare in terms of like the logic for that. But I can already do that with the floor and the ceiling though. I can define that, and then also uh, I really want to implement a um, a voxel lighting system, kind of like from Minecraft for the game, for the game engine. Um, I think that'd be really cool having lighting in a game like this. I know I've seen some. I think Z Doom. There's some sort of like lighting mod for that I've seen, and it looks really